Hi, Brennan. Take over the stage and over to you.
Thank you, Ayush. Welcome, everyone, back to the Vana Academy, the next session. Here is the overall agenda again, just to pick everyone up. Today, we will be discussing how data access works in the Vana ecosystem and the Vana infrastructure. So my name is Brennan Nunamaker. You know me from the Create a DataDAO workshop. I'm the developer experience lead at Open Data Labs. And today we have a lot of ground to cover, so I will try to go quickly, but slow enough that everyone can follow. Today we will be discussing first data refinement and how it works, then the query engine, the compute engine. We will tie everything together in an architectural overview. I will then show you the query playground that we have that makes dealing with data access a little bit easier, and finally provide you with some resources towards the end, and we can ask questions. I lied a little bit. The first slide is the simplified architectural overview so that you guys have some conceptual thing to map all of these new components to. In this diagram, we don't need to go too much into detail, but there are essentially two flows that are displayed here, the token flow in this light blue and the data flow in this dark blue. The way to think about it is you have your data contributors here on the right side of the graph. They upload their data to user-owned storage, which then gets passed on to the DataDAO, which then validates and refines the data with something like proof of contribution, and it structures it where it can then be aggregated so that compute jobs can run on this structured aggregated data inside a secure compute environment, also known as a TEE for Trusted Execution Environment. For those of you who are maybe less technical, this essentially means it's not very straightforward to just access what is inside of this secure compute environment. Like you can't just log in and look around at all of the data that's lying around. Everything's encrypted at rest, and it just makes it more secure so that it's protected against unauthorized access and even access from people running the nodes themselves. The result of the compute job, which runs on the aggregated query data, is then passed on to the data buyer, who purchases or pays for the data. Currently in Vana, it's on the roadmap to also support paying for data with ERC20 tokens and similar. That's the basic data flow through the overall system. It's fairly simplified here, very straightforward. If you look at the token flow, the data buyer purchases the data through the L1 blockchain, through the data access contracts. Some fees go to the DataDAO, and contributors are also rewarded with ERC20 tokens every time they contribute data. So just keep this in mind, that there are essentially 3 steps to go through for data access. There's the refining, the aggregating so that it can be queried, and then running computation on the query results. And we will start with the data refinement. So the purpose of data refinement is to support secure data normalization, meaning structuring it in one uniform format where the input might be unstructured on Vana data contributions. So data contributions can be files from third-party systems. It can usually be any kind of format these other third-party systems define. This refinement process allows us to kind of normalize it into one cohesive structure that queries can be run against. So that's the goal here. There are a few pieces to this puzzle as well. The first being the DataDAO data refiners. So this is what we've also seen in the Create a DataDAO workshop before. This is essentially a Docker image that can later be run inside of the refinement service that structures this data. So it takes an unstructured data point from a single file upload or similar. It can be JSON, it can be any other format that is somewhat unstructured. The data refiner that the DataDAOs build and define for their own data sets normalize this data into a structured SQLite database so that we can then later run queries against this. But this is still only one data point, remember. So it's one file that's been structured. You can also add a step to mask sensitive information like PII or personally identifiable information. This is not mandatory. It could actually impact the value of your data set if you don't do it in a good way. So it's just one thing to consider. If you do want to mask sensitive information, the data refiner is probably the place to do it. And the output of a single data refiner provided by a DataDAO is an encrypted, structured, queryable data set. Okay, so it's an SQLite database that then gets registered on chain. So once you have defined kind of how this data refiner works on a code level using maybe one of the template repositories, then you have to register it on chain with the data refiner registry smart contract, which serves as the source of truth for data refiner metadata. So all refiners that are running in the Vana ecosystem should be registered in this smart contract. It serves as the source of truth whenever we need to look something up about it. Like if we need to look up, I apologize, the schema for a refiner, which the schema is also essentially the schema of this SQLite database. Then we would look it up on chain. The schema is stored in IPFS, just some binary detail. We also have to store the refinement instruction URL on chain. This is a public URL that the DataDAO data refiner can be downloaded from. It has an owner wallet address and is associated with a DLP or a DataDAO. The next piece where these two things kind of come together is the refinement service. This is not a smart contract, and it is more general infrastructure than the data refiner the individual DLPs can define. So this service is essentially the thing that runs all of these DataDAO data refiners. It does so in a secure server environment, in a TEE, to protect the decrypted files that the user have uploaded from abuse. The DLPs trigger these refinement calls or these refinement runs through their data contributor UIs generally. So all it is an API call to a refine endpoint. This triggers running of the refiner inside of the refinement service and the results. So the results are output, which we'll see in the next step. And it loads these refiners from the on-chain metadata that we have defined here. Also to note, this API endpoint is authenticated. So most of these services in the data access, they use a form of authentication where we have a custom header field in the API request where the owner wallet, if you will, signs something relevant to that API request. So as we'll see later, for the compute engine, the authentication header will be like a signed compute job ID that's being submitted. For the query engine later, it will also be the signed contents of the query that are being submitted, etc. Just something to keep in mind is it's still safe. Not everybody can just trigger things willy-nilly. Everything is kind of locked down here. This is a very full diagram. I will walk you through it, so don't get overloaded here. But essentially, this is just a visualization of the things I've been speaking about. So the DLP data contributor UI makes an API end call to a refinement endpoint with the file to refine, with the refiner ID to refine it for. This determines the schema, and also an encryption key to decrypt the encrypted file. But this is a little bit more complicated. We won't go into encryption today, because this is more for a high-level understanding of how everything works, and a lot of our template repositories and code handle this actually automatically, so you don't really have to worry about it. So the first step is this API call is made. The refinement service, which is running inside of a TEE, gets the encrypted data file from the data registry smart contract, which is part of the Vana L1. Once the data is decrypted, it is mounted onto an input directory that is exposed through Docker for the refiner image that we are running, which we download from the data refiner registry. This is run inside of the TEE as Docker, so this Docker image doesn't have access to all of the other inputs or anything like that. It's very segmented and isolated. And after the refinement has been generated, after the data has been structured, it is uploaded to IPFS as encrypted refined data. And then the IPFS CID is output in an output folder that is also mounted to the Docker container. This CID is also stored in the data registry, so that later inside of the query engine, we can also query this refined data point for this one file and then aggregate it. But we'll get to that. Don't worry about that yet. So the next step, as we have just discussed, is the query engine. The purpose of the query engine is to support secure data indexing of all of these encrypted refined data points and querying to unlock the permissioned purchasing of Vana data. So once this data point is refined, it gets ingested by the query engine into these aggregated databases, and then later queries can run against these aggregated databases containing all of these refined data points. Okay, so that's the purpose of the query engine. There are also a few components to this. So there is a query engine smart contract. This is the source of truth on-chain for data access policies that you as DataDAO builders and DLP drivers own and define. It doesn't only mean which tables or columns or whatever can be accessed, but also which compute instructions can run. We'll see more on that later. And it also defines the pricing for individual data access queries, for example. Compute currently is not priced. The data access is pricing is resolved essentially when the query results are returned, as opposed to charging for compute and things. We will probably add this on, but it's not there yet. And the query engine is also responsible for, the smart contract is also responsible for executing payments and paying out rewards. So what does this look like inside of the query engine smart contract? There is, for example, a function, add generic permission. This is for you as DataDAO builders to add permissions for all potential data buyers. This is like a blanket permission that you can define with the refiner ID that it applies to, with the table name, this is optional, and with the column name, this is also optional, and then you can define a price. So here, this is actually 10 Vana, but this is the format of the block explorer. So we are essentially saying for someone trying to buy data for refiner ID 12, they are allowed to query the email column in the users table of our refined database for a price of 10 Vana. So if they run a query like select all emails from users, they would pay 10 Vana to access this. These policies are defined on chain. There are methods for generic permissions. There are also methods to define a price and permissioning structure for a specific consumer. So if you have a specific data buyer that wants to access a large segment of your data, but you don't want to provide this like to everyone, that's also possible. Okay, so I again encourage everyone, just as a short aside, to visit this Vana docs page with the smart contract addresses, where you can see all of these smart contracts. So for example, the query engine here, we can just go to testnet, to the block explorer, go to the contract, read write proxy, and then we can interact. We can say, okay, I want to add these generic permissions. You have to connect your DataDAO owner wallet here to define these permissions so that the protocol knows, okay, the DLP actually approved this access and not some random third party, okay? And to add permissions for a specific wallet address, you would use this add permission method. You can just look around also and see, for example, so for a given permission, for example, you can query all of this data on-chain. You can see who received this permission, is it approved, what's the refiner ID, what's the price. You can see all of this information on-chain. So I would encourage everyone to just go through these smart contracts that we've mentioned here in this call and kind of play around with them in the Block Explorer, just to get a better feel for how everything ties together. There is also a query engine service, which is another secure server environment, or TEE. And as we said, it supports secure data indexing so that it can later be queried, right? So in the query engine service, this indexing is essentially the aggregation of refiner databases. So for each refiner that is defined on-chain, the query engine listens to a set of events, namely the refinement created or something like that event. And then once it receives this event, it downloads that individual data point and aggregates it into one refiner dataset database that we can run queries against, which is also encrypted, so not everybody can just access it. And the query engine service is also responsible for running the queries against the refiner databases for data buyers. This impacts you less as DataDAO owners or builders, but it's still good to know that the query engine service is what actually runs the queries to access the data. And users can trigger permissioned queries via a query API call to the query engine service, also authenticated with the signed query contents. And it applies these on-chain access policies and these pricing that we've seen in the previous steps. So once the query is successful and the results can be accessed, the query engine automatically charges the price of that query to the wallet of the person submitting the query. So you don't have to worry about billing or anything like that. It all happens in the background automatically. And for the final piece of the puzzle, the compute engine, the purpose of the compute engine is essentially to support running computation on the computational logic on the query results in a secure environment. So this might mean, for example, somebody wants to train an AI model on data that they want to query from your DataDAO. They would do this through the compute engine. They can train the entire model inside of the compute engine, and they only have to download the model weights. And then you, as the DLP owner, for example, have prevented that they just download all of your data and sell it to somebody else. That's the main idea and motivation behind the compute engine. There are a few pieces to this. There's a question. Do you have to join the compute engine? So right now, all queries that are submitted to the query engine flow through the compute engine. This is by design to make it more secure so that people aren't pinging the query engine directly and downloading results and just leaving them on their unsecured server or something while they process it. There is, however, a compute job to kind of work around this and to mitigate the need for the compute engine. It's called a result relay compute job that essentially downloads results from the query engine and exposes it as an artifact for download in the compute engine. But you as a DLP owner have to decide, do I want to support this result relay stuff or not? So it does increase the risk of data leakage in some ways. So it needs to be decided on a case-to-case basis, but it does exist. So you do have to go through the compute engine, but you don't have to have like a complicated compute job logic that you're running inside of the compute engine. And it is safer to make data buyers work inside of the compute engine because it is a trusted execution environment. It's a TEE, so it means that all of the data is encrypted at rest, and there are additional security controls on top of that. Okay, so the first part of the compute engine cluster, as we can say, is the compute instruction registry smart contract. And what this does is it stores compute instruction metadata and compute instruction approval policies. So this is what I said where with you have to approve the result relay compute jobs, I guess, because here you're actually approving the compute instructions, where the instructions kind of serve as a template, a code template for the jobs that are later run. So you only have to approve the instruction once, and then users can submit infinite jobs with those instructions until you revoke access, which you can also do through the smart contract. Sorry, I think I got my slides switched here, but as I said, the purpose is to support secure computation on queried and purchased Vana data for ideally all conceivable use cases. Meaning, so this could mean anything from, it's a very short-lived compute job where they are just reformatting the results, the query results, into a JSON that they want to output or something like that, which would take maybe a few seconds to do. Or it could be something where they're training an AI model or they're running an inference server where it runs essentially indefinitely or a very long time. So we need to support secure computation for all of these use cases. For the compute instruction registry smart contract, which we discussed, sorry, I got my slides mixed up. We have compute instruction metadata and approval policies, which you can also see on chain. If you, for example, query the instructions with the instruction ID, you see the hash of the compute instruction Docker image just for added security so that we can ensure this code hasn't been tampered with. You didn't like approve something and then they swapped out the code and now something malicious is running on your data. But we always store this hash that we can just validate when we download the Docker image. And it also stores the owner of the compute instruction. For you as a DataDAO builder, this function will be the most relevant. So what will happen is data buyers will need to essentially prepare the compute instruction, send you the repository. You can perform an audit or have someone else do an audit. And then you can say, okay, this is safe to run on my DataDAO's data. Then you go into the block explorer, for example, and you call this update compute instruction function with the instruction that they've submitted with your DLP ID that your wallet owns, and you mark it as approved. You can also use the same function to revoke approval. The next piece is the compute engine smart contract itself, which handles the compute job registration. So for each compute instruction that we have, we can run multiple jobs at runtime without any extra approval effort. And it automatically decides which compute engine service and which TEE pool, it's called, it should be assigned to, which means it's only allowed to run inside of that environment. This is just kind of a load balancing feature. It's not too important right now. And it can also request payments, but that isn't utilized yet. So for app builders, for example, who are data buyers, they would use this function to submit a job where they define the max timeout, like how long their compute instruction job will run, and whether it requires a GPU, the difference being for training an AI model or something like that, you definitely need a GPU. And you also add in the compute instruction ID. This creates a job on chain that can then be submitted to the compute engine service. You can also kind of see which jobs are on chain by just querying them by ID or something. So whenever you create a new job, you can always go to the logs to get the job ID. I can show you that in a little bit. And yeah, it stores all of this information. So the timeout and the GPU required, these two parameters essentially decide which machine it's routed to in the background. It stores a status where it can be anything from registered to successful to failed to canceled, all of those statuses. One thing to note here is that once a compute job that has run has some kind of finalized status, like failed or something, it's not possible to resubmit the same compute job. Instead, you would need to go back and submit a new job with the same instruction ID, get a new job ID, and then you can run it again. But this is less relevant for you. And the final piece to the compute engine, I know this is a lot of information. I'm sorry, but I hope everyone can follow along. The final piece is the compute engine service, which runs the compute jobs on the query results, where the jobs themselves from inside of the compute engine TEE query the query engine TEE for the query results that can then be integrated into whatever artifacts they're trying to produce. So that could be, as I said, anything from just a JSON file that they want to download that is derived from these query results, to statistical CSVs, to, I don't know, like AI training models. And yeah, it's also a secure server, so a TE, trusted execution environment. It loads the compute instructions from the on-chain metadata. It provides produced artifacts for download, meaning all of the files that are output by the compute job can be downloaded through the Compute Engine Service API as artifacts for the job owners that have originally submitted it on-chain. It also applies execution resource constraints like timeouts, like that max timeout we saw earlier. This is applied to the Docker image so that it doesn't run indefinitely if it gets stuck or something like that. Is there a visual that shows the relation between these components and steps in the workflow for data identification, incentives definition, and exchange? So yes, there is documentation. I will show you a visual architecture tying all of this together once we get through this last part of the compute engine. And the docs have a lot of different kinds of diagrams on and documentation on different levels. So if you're looking for more details, you should look in the docs. We are still reworking some things, so it might not be 100% accurate right now, but it should be within the next 1 to 2 weeks, I would say. I mentioned before that the Compute Engine Smart Contract determines which service machine and TE pool to assign it to based on the max timeout and GPU required parameters when submitting the job. This is what these TE pools are. So these exist as smart contracts on the chain. I won't go into too much detail here, but it's just good to know that depending on the max timeout, so for example, if you set less than 5 minutes, I think it's 300 seconds because this parameter is in seconds. Then it will be assigned to an ephemeral standard machine. Persistent standard are just designed to support more long-running tasks that may take up to 2 hours. There's a CPU variant and a GPU variant, and then there's a dedicated standard pool that also has GPU. It's not time limited at all, but it's just good to be aware of this. It probably won't interact with this very much. Do you use Fala's attestation service or GPU providers like NVIDIA for a dedicated single GPU? That's a great question. So we do currently run our TEs on the Fala network. It's just a service provider for TEs. Their GPU machines are NVIDIA GPUs. So I think this is also the most common for machine learning currently. So most training jobs should be covered by that, but it is possible to define or register other TEs that could have other GPUs or something like that. We might need to make some code changes, but it's possible. And as far as attestation goes, I'm not 100% certain what the current status is on that, so I'd have to get back to you. But if we haven't done it yet, tough. Yes.
I can comment on the attestations. Yeah, so Follow Cloud provides attestations out of the box, but we don't propagate them on chain or require them at any point. We do have a plan to have more general attestations available in the L1. And it won't be just specific to Follow Cloud. Like when we expand where our TEs come from outside of Follow, we'll need a more generalized attestation solution. So we'll be working with Follow to make that possible.
Thanks, Kataf. I would also say if you have any kind of like special requirements that we can't currently model around hardware or something like that, you can work with us and we'll figure out a solution. So don't stress about that. And now to tie everything together, I'll present an architectural overview with all of the components. So the way to read this diagram is essentially we have our application builders or data providers up here. They may want to do different things like train an AI agent, perform some industry analysis, or even sentiment analysis on specific data. What they do is they submit a compute job to the compute engine. So that's visualized here, where this has an aggregation job, this has an AI training job, this has a query job. These interact with the compute engine and compute instruction registry smart contracts primarily, just to make sure that everything is above board as far as access permissioning, policies, payments, all of that. The jobs themselves run queries against the query engine, which has these aggregated refiner databases. So depending on whatever DLP you're building, whatever kind of data you have, your refiner will end up in one aggregated database in the query engine that they can then run queries against according to the permissioning policies. And the query engine mostly interacts with the query engine smart contract. So this is like the data buyer perspective of how they run through it. The other half of the equation is data contribution and data collection. So we've seen this in a few different variants before, but here you can see at the bottom we have the data contributors contributing their raw data through your DLP's data contribution UI, which usually encrypts it locally in the browser, I believe, and uploads it to user-owned storage. This is written into the data registry contract. and also the file is passed on to the DataDAO, which runs it through the refinement service and the Satya Prover network. This Satya Prover network is for the proof of contribution, which we can see here as the data proof, which is then also written into the data registry. And for the refinement service, it produces refined data that gets written to IPFS and then also written to the data registry. So the refinements are also stored in the data registry. That's an important detail. The data refiner registry here is linked to visualize that the refiner image that runs inside of the refinement service is fetched from that contract.
I have a quick question.
Sure.
The compute for all this,
Yes.
who's paying for that? Or is that built into the price of Vana? Or is that like, or am I missing something?
No, currently we don't charge for compute. We
Okay.
only charge for data access. We do have it on the roadmap to add charging for compute to this whole flow, but right now we are essentially sponsoring this from inside of our TEs.
Okay.
Okay, makes sense. Or I think other people should also theoretically be able to run TEs. No, they aren't doing it yet. In that case, whoever's running it would be sponsoring it as well. But there will be a lot of changes coming up soon, so don't get too stuck on this. We're still very early. Okay, any other questions around the overall architecture and how these pieces fit together? Maybe now's a good time to pause and see. I don't see anything in the chat. So there is a tool that we can use to kind of visualize this whole data access flow. It's also fairly useful for like debugging your refiner image or things like that, checking if the permissions on chain are valid and all of the configuration stuff you have to do around this. The playground won't expose all of it, but if you can successfully query data here, you should be able to assume that everything is working. So this is at playground.vana.org. It defaults to the Moksha query tester. You can switch to mainnet. You do have to connect a wallet, which I've already done. And the way that this works is you specify the compute engine TE URL. There are currently only two, one for Moksha, one for mainnet. They should be documented somewhere. If you can't find it, just ping us and we'll see why you can't find it and give you the URLs. You provide a compute instruction ID and a refiner ID and then a query that you can submit, and it should go through the whole flow of creating a compute job for this compute instruction, writing it on chain, submitting it to the compute engine API. The job itself, this compute instruction, is actually the result relay compute job that I mentioned earlier. So all that it should do is basically return the results that the compute engine was able to download from the query engine as an SQLite database. So that should be the whole flow. Yeah. So it's also like creating all of the authorization headers that we need, like signing the query contents, signing the compute job ID that it generates from this compute instruction. But if there is a misconfiguration somewhere here, this will likely fail. We can just try it out. So I have to confirm a transaction to submit the job on the blockchain. There should be some there's another request. We can just confirm. This is the query that it's signing. So the one before that was probably the job ID. That's why it was just a number. And now it's submitting it to the API. The compute job has been created with this job ID. There is a run ID. In case there are certain cases where you can submit a compute job multiple times. So that's why there's this run ID. So you can kind of map out, okay, I had this job, but what was the run? And okay, so the job was successful. We can download the results. and there is a query results database. So usually what you can do, I'll stop here, but usually what you can do with this SQLite database is you can just use the SQLite 3 CLI tool to go in and look at the actual records that were downloaded. And you can use this to kind of debug what is the query returning for this compute job. Okay, so it's just a useful tool to have. Good to know that it exists. And that's pretty much it. There are additional resources. There is a Vana CLI that's currently in alpha. There is the Discord, which you guys are familiar with, the docs that you're also familiar with, and there are some code templates to kind of look around and play around with all of these things. So there's the data refinement template, which is essentially for you as a DataDAO. When you are trying to refine your data, you can use this as a jumping off point. There's also a compute job template where the app builders and data buyers can use this as a jumping off point for their compute jobs. There's also the result relay compute job. So if you don't know where this compute instruction is registered on chain, you can just go in and register it yourself and write the on-chain approval with your DLP wallet through the block explorer. For the instruction that you have registered, you'll need the ID. And that's pretty much it. So any questions, anything we should go through again? I know it's fairly complicated. There are a lot of moving parts, but I hope it was easy to digest.
I have a question. So the data that I'm potentially going to be building with is kind of complex and vast healthcare data, medical record healthcare.
Mm-hmm.
So when it gets into that SQL phase, it's pretty complex. So like many tables, and I'm just wondering, I'm thinking out loud about what that's going to be like using SQLite, or if it's potentially, if there's a pre-step involved. I guess I'm just thinking out loud at this point.
So the database that's created here for your refiner that you have created, this is created with the schema that you specified originally when registering the refiner. So it's very early on, but here when you're registering your refiner in the data refiner registry, you also have to provide a schema definition URL, which is in IPFS. So that gives you like control over all of the tables and things that you want to build. It should also give you control over like defining indexes and things like that.
Okay.
Yeah, and it's also, I think, completely valid to have multiple refiners for one given DLP. I don't think anyone is doing this yet, but if, for example, you wanted to have 3 separate data sets with different levels of PII or something, personally identifiable information, then you could hypothetically do that. We might have to work out some of the kinks, but it should work.
Cool. Thanks.
Okay, sure. There's another question. Where is the match for a data buyer to data prover happening? Which contract is that? The way to think about that is, so currently the assumption is a little bit that all of the negotiations will be happening initially offline, maybe through Discord or Telegram or something like that. And you have to just coordinate with the data buyers around which compute instructions do they need to use, which query access permissions do they need, and what price are you going to charge them for those queries. And then once you have that information, you need to provide approval for their compute instruction through the compute instruction registry smart contract. And for the query access permissions and pricing, that would be through the query engine smart contract. So here we have like this add generic permission example, but if you're negotiating with a buyer that wants to buy a lot, you would use the add permission example, and you can specify their wallet address. We will be building out this infrastructure as well to provide more like out-of-the-box matching mechanisms, I guess you could say. So just keep an eye open for that. And there's another question. Data or online theft happens all the time. Is the process created foolproof against this, or makes it hard for people to steal data or tokens? That's also a good question. So essentially, there are a lot of protections in place. Like we process everything inside of the TEEs. Everything has these authentication mechanisms where if you are not the right person trying to access something, you get rejected. But there's still a level of responsibility that the DataDAO itself and the DLP itself needs to take. And that's why we have all of these access controls as well. So for example, it is still kind of on you to make sure, okay, is this person I'm selling data to, are their compute instructions potentially malicious? I would assume mostly not, but always check if you can. Like the code repository should be public so that you can verify that. And the other issue is so you have these access controls on the table and on the column level, or you can define these permissions and pricing for like the entire refiner. If there are no permissions, for example, for refiner ID 12, then nobody can query data from them, meaning you do have very fine-grained control over who accesses what through these mechanisms, and you should make use of them where possible. Great, I don't see any more questions. Then I think we can probably end it here. Thank you everyone for taking the time. If you do have follow-up questions around these concepts, because there is a lot of information here, like just ping us on the Discord. I'll try to answer them as quickly as possible. And there are also a lot of pages in the docs that you can look at and kind of play around with the smart contracts as I've recommended, and you should get a hopefully better feeling for this. Thanks, everyone.